Today, I'm going to talk about grading starvation, learning proclivity in neural networks. It's a joint work with Omar, Yashua, Aaron, Doina, and Gume. So Gume is here with us today, and he is one of yours, I believe. He's done his graduate studies here at the University of Washington, right?
Yeah, that's right.
All right, so let's start with a little bit of history. So back in 1904, there was a horse called Hans, and so people believed that he could do arithmetic. Here's an article from New York Times published in 1904. It says that Hans is an expert in numbers. So for example, when two numbers of 5 and 9 are written on a blackboard, Hans would have replied by tapping on the ground like 14 times. So 7 years later, in an article, Oscar Funst unveiled that the so-called clever Hans was not actually capable of doing any arithmetic. And indeed, it was reading subtle hints in his trainer's behavior, indicating when to stop tapping, essentially. So as the article says, that even the trainer himself didn't know that he was providing the horse with these shortcut signals. So this phenomenon in psychology is often referred to as the clever hands effect. And this talk is about spotting this effect in neural networks and understanding why this happens. All right, so now that we have some idea about the problem, let's outline the structure of this presentation. So we are going to go through some instances of this clever hands effect in neural networks. And then we introduce grading starvation as a cause for this phenomenon. We then look at the quick theory of a quick look at the theory of this grading starvation, and we try to provide a remedy. Finally, we go to the experimental results, and we then finish the talk with hopefully a long discussion. All right, so instances. So I'll try to manage my time to spend half of my time on this part and the other half here. So probably we have enough time for discussion, but I'm happy to take questions through the presentation if we don't get too derailed. Yes, so please do not hesitate to interrupt me. So a similar phenomenon has been observed in neural networks. I mean, this clever hands effect that the network or the model or the horse latches on some form of features, spurious features that do not actually generalize and do not capture the underlying factors of variation. So in a rather recent paper by Robert Gareth et al., they basically list some tasks in machine learning that shows such a phenomenon. For example, in this task of image captioning, the network predicts like grazing sheep by just looking at the background, looking at the green hillside. So in another task, so here the model, like with high confidence, predicts a teapot in this figure, which is like pure noise. In another very famous and indeed dangerous task of pneumonia detection from X-ray images, the model seems to perform actually very well on even the test set, but the heat maps reveal that the model is indeed only looking at the corner of the image with some spurious correlations and not looking at the lung itself at all. So the intuition behind this phenomenon is a faulty knowledge in one way or another. Essentially, given a strongly correlated and fast to learn features in training data, grading descent is biased towards learning them first. So although the idea is kind of, the intuition is kind of like understandable to everyone, this intuition is still a bit abstract and hand-wavy. So let's look at a more concrete example that helps in formalizing the grading of starvation. So consider a simple 2D classification task of this red data points versus the blue data points. If we train a neural network on this, here's the learned decision boundary. So we learn a curved decision boundary. Now consider like a slightly different arrangement of the data points in which the blue data points are shifted to the left just a little bit, and the red ones are shifted to the right just slightly. So, but this like simple change in the arrangement of the data points results in a very different learned decision boundary. So we observe that the decision boundary is almost linear and only basically discriminate based on the x feature, the x-axis feature, and remain invariant to the variation of the data along the y-axis. So we argue that grading starvation is responsible for this behavior. So grading starvation essentially is a phenomenon in which a neural network learns to capture statistically dominant features while remaining invariant to the rest. Here, gradient descent leads to parameter updates predominantly in the directions that only capture these dominant features, and thus starving the gradient from other potential informative information. Okay, so in this simple example, as I said, just learning to discriminate the two classes only along the x-axis basically brings the loss to a pretty small value, to 0 indeed, and makes the network overconfident on its predictions, while not learning to discriminate along the other axis. So what are the consequences of basically such a phenomenon? So an immediate consequence is lack of robustness to adversarial examples, as well as poor generalization, out of distribution generalization performance. So probably all of you are familiar with adversarial examples like an image that is classified as panda with a small, with a little bit of perturbation is now classified as gibbon with a pretty high confidence. So essentially, like mapping this to this 2D example that we have, we noted that the decision boundary is pretty close to the data points. So by just perturbing one data point just slightly to the left might get an example that is classified as the wrong class with pretty high confidence. So essentially, the slope on the decision boundary here is very large, and the network it's a very high Lipschitz function. So another consequence that has been reported in a paper by Jacobson et al. From Vector Institute, it's basically a similar problem, but kind of different. It's the excessive invariance. Okay, so in this paper listed here, authors show that, for example, these two images, although very different, they result in the exact same Logit's distribution. So essentially, the network, the hidden representation of the network for these two images or these two are very basically are exactly the same. And so again, to map it to this 2D example, I would say that if we take an example here, for example, then this image has pretty high probability of being classified as red under the network distribution, while it has a pretty low distribution under the probability of the data. So the last consequence, so of course there could be lots of consequences, but so these are the three that we mentioned here. So the last one here is the implicit regularization. So one might argue that according to the Occam's razor, learning a simpler decision boundary, a simpler solution should actually is better, and this solution should generalize better. So that is both right and wrong. So to answer to this question, it depends on the distribution, our assumption about the distribution of the test set, whether it is IID or OOD. But we're gonna leave it for now and then come back to it at the discussion part. So I am about to dig a bit into the theory. So if there is any questions so far, I think maybe it's a good time to take a few questions. All right. So so these notions of features and the dominancy of a feature is rather vague. So to define them more formally, we need to look into the learning dynamics. So in the interest of the time, I will be covering only the gist of the theory. So please refer to the paper for a detailed treatment. Now consider a neural network, F, like the neural network that we have here, with the input X and parameters theta. And the loss function is binary cross entropy if the task is a binary classification task. So, and the output of the network is y hat, right? So if we do gradient descent, here's the update that we get. So theta at time t minus theta at time t minus 1 is equal to the negative of the gradient of the loss function with respect to the parameters. So with taking the limit of infinite small learning rate, we get this continuous time limit, which is theta dot, which is just the derivative of theta with respect to time, equal to the gradient of loss with respect to theta. All right, so if we apply the chain rule on this term, we will have these two terms. Just a second, let me close my Telegram because it's distracting me. All right, so there are two terms here from the chain rule. The first term is the gradient of loss with respect to output, and the other one is the gradient of the output with respect to the parameters. And both of these terms are nonlinear, and they changes over time, and they make the understanding of the dynamics pretty complicated. So to get rid of this term, basically to make this term simpler, we apply the neural tangent kernel on the function. So the neural tangent kernel is nothing but a first order Taylor approximation of the function. So if we linearize the network around its initialization, then we end up with y hat equal to a matrix phi, matrix of like what they call it, neural random feature matrix, and theta as the a vector containing all the parameters. So the phi here would be the gradient of output with respect to theta. So basically phi contains like a matrix of random features for all the training examples. So thanks to the neural tangent kernel, we have the guarantee that the parameters do not change, and basically the kernel and the random feature data matrix does not change much over time, so we can assume that it is fixed. So essentially, the gradient of output with respect to theta would be just the fixed matrix of T, the matrix of phi, which is constant with respect to time. But there's still another term remains, which is the gradient of loss with respect to y hat. Okay, and that is just like a sigmoid function, right? Like an inverse sigmoid. That so the more confident the network is, So y hat shows how confident the network is on its predictions. So because like y could be +1 or -1, and y hat is simply the linear output of the network. So the more confident the network is, the less gradient we receive, because the inverse sigmoid, it saturates, all right? So let's look at the dynamic in it and see how basically how it works. So we apply a singular value decomposition on phi, and it would be U S V transpose, which the matrices of U and V transpose, they are both orthogonal. So here we call the directions, so basically the columns of V, to be features, S, like each S to be a strength of that feature, and a column of U basically to represent the mapping between that feature and the examples containing that feature. All right. So here, if we multiply both sides from right by V, then V transpose V cancels, and we end up with this. So we call this theta dot V Z. Okay, this is the change of variable that we make. And Z's basically essentially are the response of the network to any of the features that we have in our neural tangent kernel. All right, so we have summarized it in the next slide to make it basically more understandable. So the NTK, the neural tangent kernel, is the matrix phi, which is the gradient of output with respect to theta at the initialization time. We apply a singular value decomposition on phi, it would be U, S, and V transpose. Each column of V, indicated by VI, is a feature. We call it a feature. Its strength is represented by SI, basically the diagonal elements on S. And so the correlation with the label is indicated by Y transpose UI, because as I mentioned, UI basically represents like how much of these feature is contained in any of the examples. So the dot product basically shows the correlation with the label. And what we are interested at is the response of the network to any of these features. So since the network is linearized, so by just multiplying that feature by theta, we get the output of the network when only that single feature is present. All right. So we are interested to know how ZIs evolve over time. All right. So here's the intuition of our main results. Look at the plot on the right. On the x-axis, we have the iterations, and on the y-axis, we have two features of Z1 and Z2, or to be more precise, Z1 and Z2 are the response of the network to that feature. And if you want to know how the response of the network to those features basically evolve over time. So for this particular example, it seems that basically V1 or Z1 is more correlated with the label. So it is learned that much at the end of the training, while the other feature is learned this much, okay? But the speed of learning is determined by S, how strong that feature is. So when the speed of learning of these two are basically essentially the same, so the slope that they start with is the same, but this converges to like a higher place. Z1 converges to a higher place because it's more correlated with the output. Now let's see what happens if we keep the correlation fixed. We also keep the strength of the second basically feature fixed, but we increase the strength of the first feature. All right. So again, S2 is 1, but this time S1 is equal to 2. So we observe that so the learning along S1 is faster, along Z1 is faster because its corresponding singular value is larger, but it is being overestimated essentially, while the other feature is underestimated. So we can see a drop here while an increase here. So as we increase, basically the value of S1 So we can see that S1 is learned faster and also to a larger value. And at the same time, although S2, basically the strength of S2 hasn't changed, and basically the correlation of the S2 with the target has not changed, it has remained constant. But the response of the network to that S2, basically to Z2, decreases. All right, while this is basically we have a rich gets richer effect here, and poor gets poorer effect, essentially. So this is what we call grading starvation, a little bit more formally. So we looked at the dynamics and tried to understand basically where this coupling between different features is introduced in the dynamics. And so we try to decouple that coupling and end up and reverse engineer that term to the loss function, trace it back to the loss function, and see what should we add to the loss function in order to decouple the learning of different features. And it turned out to be a very simple term. And that very simple term is simply the L2, the norm of the output of the network. So usually what we see here is instead of y hat here, we have theta, and that would be L2 on the parameters, the weight decay. But here we suggest that instead of weight decay, apply an L2 on the output of the network. So on this simple example, let's see what happens. So we can see that as we increase the value of S1, the place that they converge to, the fixed point of the dynamics, are now decoupled. They're not a function of basically S1 and S2 anymore. So this is exactly what we were looking for, essentially decoupling the fixed point of the dynamics. So an increase in the strength of like a feature does not affect the learning of another feature. All right. Okay, so okay, before going to the experiments, is there any question here? All right, looks good. Now let's look at the experimental results. So recall the example, the 2D classification task that we had. So this is when the data is not linearly separable and the learned decision boundary is curved. So on the right here, we can see how Z1 and Z2 evolve over time. So this is, I hope it is clear for you. So this is Z2 and that is Z1, and how they evolve as we train the network. So if the data is linearly separable, meaning that again, we have shifted the blue one to the left a little bit and the red class to the right a little bit, and then the learned decision boundary is almost linear. Let's see what happens in the space of the features. We can see that now Z1 is captured much more than before, while Z2 is almost not captured at all, right? And now let's see what happens when we add a spectral decoupling to it. So we can see that the spectral decoupling results in like suppressing Z1 and basically decreases Z1, and that decrease in Z1 allows Z2 to basically to grow. So look at the solid ones. So now both Z1 and Z2 are learned, and in terms of the decision boundary, we can see that the learned decision boundary is curved and basically is discriminating the two classes along both axes. So we also basically in the paper we note that other regularization methods or training schemes does not seem to help with learning a curved decision boundary. All right, so in this task, in this 2D one, we learned that ST results in, by ST again I mean a spectral decoupling, our proposed method. spectral decoupling results in learning like a larger margin classifier. So does that happen in more real-world tasks? So here we have a task on CFAR classification. So this is a binary classification of CFAR. We have two classes. So basically, essentially, the first 5 classes of CFAR would be class 1, class 0, or the other half would be class 1. So we apply a nonlinear network, a four-layer convolutional neural network on that. And we want to know whether like adding SD to the loss would basically make the model more robust. Basically, does it increase the margin or the distance of the data points from to the decision boundary? So for a nonlinear decision boundary, it is not trivial how to basically compute the distance to the decision boundary, but as a proxy, we can look at like how much perturbance is needed in order to basically cross the decision boundary. So how much noise should I add, or basically like not any noise, basically a noise coming from like an adversarial attack. How much of that noise is needed for this example in order for it to cross the decision boundary and being misclassified? Okay. So this plot on the right essentially is showing that. So on the x-axis, we have the norm of the disturbance, and on the y-axis, we have the misclassification percentage. For example, for a specific value of disturbance, like for a specific attack, we can see that almost all the examples of a model trained with binary cross entropy is misclassified, almost 100%, while much less basically percentage of the examples are misclassified when trained with spectral decoupling. So is there any question on this plot? Okay. So in another example, in another experiment, we looked at the color dimness task. So it's a task of, again, binary classification. Digits of MNIST are, so digits of 0 to 4 are basically class 0, and 5 to 9 are class 1. So this task was first introduced in the invariant risk minimization paper of Martin Arjovsky et al. So the setup is as following. There are two training environments. One training, in the training environment number 1, the color is positively correlated with the label in 90% of the situation. Okay. So again, so this is a color dimness. So an artificial color channel has been added to each image. So the digits could be green or red. So in training environment number 1, so in 90% of the situation, it is positively correlated, meaning that the green correlates with class 1 and red correlates with class 0. In training environment number 2, we still have this positive correlation, but with 80% basically probability. However, in the test environment, the color is negatively correlated with the label with 90% probability, meaning that, so if we train a network on the training environments and it only learns the color, it's gonna fail very badly on the test set, because in the test set the color is reversed. So also 25% label noise is added to the data. So an oracle would possibly get 75% accuracy. Okay, so here's let's look at different models and see what they get. So because this is a binary classification task, a random guess would give us like 50% accuracy only. So ERM, expected risk minimization, which is the model that we use in our models, like binary cross entropy, it gets 87% on the train, very good, but it gets like 17% on the test which is very bad. And it is not basically, we should not be surprised, as I said, because so the color used to be positively correlated in the test set, in the training set. Now it's negatively correlated in the in the test set. So how should one expect the model to basically perform well? So at the same time, we can see that the IRM, the invariant risk minimization, it performs very well on the test set and basically reasonably on both the test set and the training set. And so we know that the IRM actually uses the signal, the supervised signal, that the data is coming from environment number 1 or environment number 2. So because the amount of correlation between the color and the label is different between the two environments, invariant risk minimization uses that as a form of signal to eliminate the color feature. So now let's look at our model, which is spectral decoupling. So we can see that it also performs very well on the test set as well as the training set. However, it doesn't need, at the same time, it doesn't need to know about basically environment 1 and environment 2. So we essentially aggregate both environments, and we end up with an environment which is which the color is correlated with the target in 85% of the cases, and we still perform very well on the test set. So we have a little bit more like experiments on this, trying to understand why that is the case. We might get back to this if we have enough time, but I'm gonna move on for now, and then in the discussion we might come back here. Okay, in the final task of in the final experiments that we basically tried our spectral decoupling on is the task of hair classification. So the idea is the task is to classify people like images with blonde hair or dark hair. However, there is some spurious correlation here that most of the blondes are female and most of the dark hairs are male. So, and only a small percentage of the data set are like blonde male. So for example, in the celeb A data set, less than 1% of the images have this feature that males are blonde. So if you train a vanilla cross entropy on this, we get 90%, 94% accuracy on average, which is very good. But on this worst group meaning this group with blonde male, or I believe it also contains like dark hair females. So we get 40% accuracy, which is worse than random. So another paper, which is group DRO, distributionally robust optimization, it achieves 87% accuracy on the worst group, but it requires the knowledge that oh, this is the rarest group, this is the worst group. So what it does basically, it has the supervision signal on these examples and multiply the gradient of the examples coming from this class, coming from this group by like a large number, so forcing the model to put more emphasis on these examples as well. So at the same time, we can see that the spectral decoupling, without having any supervision signal, it achieves 83% accuracy on the worst group. All right, so I think that's it for the experiments. Here are the final remarks. So we learned about the clever hands effect. We also learned that a similar phenomenon has been observed and reported in neural networks, and we hypothesized that grading starvation is the primary cause, or at least one of the reasons behind this phenomenon. And so to understand to formalize grading starvation and to understand feature learning, we looked at the learning dynamics. And we show that with cross-entropy, the presence of a strongly correlated features could result in a starvation of other features. We also try to find a remedy, which we call a spectral decoupling. And we show that this spectral decoupling basically allows the learning of different features to be decoupled, and in practice, it appears to improve like over many tasks. So that's it. Thanks for your attention, and I hope that no gradients will be starved.